This video covers the discovery of the atom structure. The initial idea that matter is made up of small indivisible particles is common to many ancient cultures across the world. The Greek philosophers Leucippus and his student Democritus from the 5th century BC are credited as the founders of atomism. The atom, which means uncuttable or indivisible, is the smallest unit that cannot be further subdivided. Leucippus and Democritus divided the world into two entities: atoms, indivisible particles that make up all things in the world, and the void, the nothingness that exists between the atoms. The Greek philosopher Empedocles established the theory of the four classical elements: fire, air, water, and earth, which would combine to form atoms. He also proposed forces he called love and strife, which would mix and separate the elements respectively. John Dalton was born on 5 or September 6, 1766 and died on July 27, 1844. He was an English chemist, physicist, and meteorologist. Dalton introduced atomic theory into chemistry. He was colorblind and studied the topic, and as a result, color blindness is known as Daltonism in several languages. He also tutored the young James Prescott Joule. In the early 19th century, he noticed that chemical elements seemed to combine with each other by discrete units of weight, and he decided to borrow the Greek word atom to refer to these units. Dalton experiments showed that water was produced by mixing hydrogen and oxygen in the ratio of 1:8 mass units. He concluded the oxygen atom was 8 times heavier than the hydrogen atom and stated the water formula should be HO, representing 1 atom of hydrogen and 1 atom of oxygen. Joseph Louis Gay-Lussac Voss, born on December 6, 1778 and died on May 9, 1850. He was a French chemist and physicist. Gay-Lussac conducts similar experiments to John Dalton but analyzed them on a volumetric basis. He concluded that 2 volumes of hydrogen gas combined with 1 volume of oxygen gas produced water, and therefore concluded the water formula should be H2O. John Dalton and Joseph Louis Gay-Lussac were contemporaries, and we can only imagine that the results from their experiments seemed to contradict each other. Lorenzo Romano Amadeo Carlo Avogadro di Quaresca e di Certu was born on August 9, 1776 and died on July 9, 1856. He was an Italian scientist. Avogadro came up with the concept of molecules. Avogadro explained that the hydrogen molecule H2 is composed of 2 hydrogen atoms H, oxygen molecules O2 are composed of 2 oxygen atoms O, and water molecules are composed of 2 hydrogen atoms and 1 oxygen atom. This explained that results from Dalton and Gay-Lussac were both correct, but one was expressing a mass relationship and the other was expressing a molecular relationship. He determined the correct weight of oxygen atom to be 16 times the weight of the hydrogen atom, and that the correct formula for water is H2O. The Avogadro constant is one of the 7 defining constants of the International System of Units. Up to most of the 19th century, the atom was still seen as the smallest unit of matter that cannot be further subdivided. Joseph John Thomson was born on 18 December 1856 and died on August 30, 1940. He was a British physicist. Thomson was awarded the 1906 Nobel Prize in Physics for his work on the conduction of electricity in gases. He was a professor at Trinity College, Cambridge, and 7 of his students went on to win Nobel Prizes. Ernest Rutherford, Chemistry 1908, Lawrence Bragg, Physics 1915, Charles Barkla, Physics 1917, Francis Aston, Chemistry 1922, Charles Thomson Rees Wilson, Physics 1927, Owen Richardson, Physics 1928, and Edward Victor Appleton, Physics 1947. His impressive list of students also include John Strutt Rayleigh, Niels Bohr, Julius Robert Oppenheimer, Max Born, among many others. In 1897, Thomson was working with cathode rays. Cathode rays are produced when a voltage is applied to 2 electrodes in a vacuum tube. This was used in early television sets and oscilloscopes and neon signs. Thomson observed that cathode rays can be deflected by electric and magnetic fields, and therefore concluded the rays were made of particles. Thomson measured these particles to be 1,800 times lighter than hydrogen, which is the lightest atom. He called these new particles corpuscles, but they were later renamed as electrons. It was quickly recognized that electrons are the particles that carry electric currents in metal wires as well. Thomson concluded that these electrons emerged from the atoms of the cathode in his instruments, which meant that atoms are not indivisible as previously thought, but the name atom stuck. He proposed the atom was like a plum pudding with electrons surrounding a volume of positive charge, like negatively charged plums embedded in a positively charged pudding. Since classical times, it has been known that some materials, such as amber, attract lightweight particles after rubbing. There are many examples of electrostatic phenomena, from those as simple as the attraction of plastic wrap to one's hand after it is removed from a package, to the apparently spontaneous explosion of grain silos, the damage of electronic components during manufacturing, and photocopier and laser printer operation. William Gilbert was born on May 24, 1544 and died on November 30, 1603. He was an English scientist. Henry Cavendish was born on October 10, 1731 and died on February 24, 1810. He discovered hydrogen and also determined the density of the Earth, and was able to calculate the gravitational constant. In 1600, Gilbert used the word electron, Greek for amber, to refer to the property of amber attracting small objects after being rubbed. This is the source of the word electricity. In the early 1770s, Cavendish wrote,
"We may therefore conclude that the electric attraction and repulsion must be inversely as some power of the distance, and there is no reason to think that it differs at all from the inverse duplicate ratio."
He was proposing that the attraction and repulsion electric force should have a similar formulation as Newton's law of universal gravitation. Charles Augustin de Coulomb was born on June 14, 1736 and died on August 23, 1806. He was a French physicist. He did important work on friction and determined an expression for the force of electrostatic attraction and repulsion. The SI unit of electric charge, the coulomb, was named in his honor in 1880. In 1785, Coulomb published his first 3 reports of electricity and magnetism where he stated his law. This publication was essential to the development of the theory of electromagnetism. He used a torsion balance, similar to the one used by Cavendish to study gravitation, to study the repulsion and attraction forces of charged particles, and determine that the magnitude of the electric force between 2-point charges is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. This became known as Coulomb's law. The force between 2 particles of charge Qt and Q separated by a distance d is given by. The electric field is created by particle Q is defined as yielding the force on a test particle as. We know now that this is valid only for stationary particles, therefore the term electrostatic is used in reference to Coulomb's law. Ernest Rutherford was born on August 30, 1871 and died on October 19, 1937. He was a New Zealand physicist. He is considered the father of nuclear physics, and you will see why. In 1908, he was awarded the Nobel Prize in Chemistry. His discoveries include the concept of radioactive half-life, the radioactive element radon, and the differentiation and naming of alpha and beta radiation. In 1917, he performed the first artificially induced nuclear reaction by conducting experiments where nitrogen nuclei were bombarded with alpha particles. As a result, he discovered the emission of a subatomic particle which he initially called the hydrogen atom, but later, more accurately, named as protons. Some of his famous students' accomplishments include Edward Victor Appleton, Nobel Prize winner and pioneer in radiophysics. James Chadwick was awarded the 1935 Nobel Prize in Physics for his discovery of the neutron in 1932. In 1941, he wrote the final draft of the Maud Report, which inspired the US government to begin serious atom bomb research efforts. He was the head of the British team that worked on the Manhattan Project during World War II. Norman Feather proposed that the 239 isotope of element 94, plutonium, would be better able to sustain a nuclear chain reaction. Cecil Frank Powell Nobel Prize in Physics laureate for heading the team that developed the photographic method of studying nuclear processes and for the resulting discovery of the pion, a subatomic particle. Henry DeWolf Smith played a number of key roles in the early development of nuclear energy. As a participant in the Manhattan Project, a member of the U.S. Atomic Energy Commission, and U.S. Ambassador to the International Atomic Energy Agency. Ernest Thomas Sinton Walton Nobel laureate who first split the atom. He is best known for his work with John Cockcroft to construct one of the earliest types of particle accelerator, the Cockcroft-Walton generator. In experiments performed at Cambridge University in the early 1930s using the generator, Walton and Cockcroft became the first team to use a particle beam to transform one element to another. Yuli Borisevich Khariton was a Soviet physicist who was a leading scientist in the former Soviet Union's program of nuclear weapons. Niels Henrik David Bohr made foundational contributions to understanding atomic structure and quantum theory, for which he received the Nobel Prize in Physics in 1922. Johannes Wilhelm Geiger, best known as the co-inventor of the detector component of the Geiger counter. He also proved the existence of isotopes of certain radioactive elements. In 1921 he received the Nobel Prize in Chemistry. Frederick Soddy together with Ernest Rutherford explained that radioactivity is due to the transmutation of elements. He also proved the existence of isotopes of certain radioactive elements. In 1921 he received the Nobel Prize in Chemistry. Otto Hahn, a pioneer in the fields of radioactivity and radiochemistry. He is referred to as the father of nuclear chemistry and father of nuclear fission. In 1938, Hahn, Lisa Meitner and Fritz Strassmann discovered nuclear fission, for which Hahn received the 1944 Nobel Prize for Chemistry. Marcus Lawrence Elwin Oliphant played an important role in the first experimental demonstration of nuclear fusion and in the development of nuclear weapons. An impressive list of accomplishments from Rutherford students, who himself was a former student of Joseph John Thomson that had an impressive list of past students as well. Rutherford formulated the first modern model of the atom in 1911. He proposed a very small, positively charged nucleus, containing much of the atom's mass, was orbited by low-mass negatively charged electrons and that most of the space of the atom was empty space. The electrostatic attraction between the negative electrons and the positive protons acted in a way similar to the force of gravity that keeps the Moon orbiting the Earth. The Coulomb constant Ke was replaced by the permittivity of free space epsilon O. The electrostatic force then can be written as: for a single electron orbiting a nucleus of an atom with atomic number Z, the electrostatic force on the electron is. But this force must be equal to the centrifugal force on the electron. Therefore, the following equation can be written. Or solving for the orbital radius yields. The electron has a total energy that can be broken into a kinetic component and a potential component. The electron kinetic energy is trivial. And the potential energy is defined as the work done to bring a particle from infinity to a certain radial position r, which yields. The total energy is therefore the sum of kinetic and potential energies. And the orbit radius can be expressed in function of the total energy E, as. Finally, Rutherford model for the atom is written as. Rutherford model has two main problems with experimental evidence. The first is that when charged particles are accelerated, they emit electromagnetic radiation. Since the electron is constantly being accelerated around the nucleus, it would continuously emit radiation, losing energy, and follow a spiral path and collide with the nucleus. The second and more subtle problem is that atoms do emit electromagnetic radiation under some conditions. This happens at very specific frequencies. It was thought that this was due to the electron changing its orbit, but there was no explanation for why this occurs at discrete and specific frequencies. Light always intrigued scientists. It wasn't until the late 17th century that scientists began comprehending light's properties. We are already very familiar with Isaac Newton. He also made important contributions in understanding the nature of light. Christian Huygens was born on April 14, 1629 and died on July 8, 1695. He was a Dutch mathematician, physicist, engineer, astronomer, and inventor who is regarded as a key figure in the scientific revolution. Huygens made seminal contributions to optics and mechanics, and astronomy. As an engineer and inventor, he improved the design of telescopes and invented the pendulum clock, the most accurate timekeeper for almost 300 years. Isaac Newton proposed that light was made of tiny particles, while Christian Huygens believed that light was made of waves propagating perpendicular to the direction of its movement. In 1678, Huygens proposed that every point that a luminous disturbance meets turns into a source of the spherical wave itself. The sum of the secondary waves, which are the result of the disturbance, determines what form the new wave will take. This theory of light is known as the Huygens principle. Using the above stated principle, Huygens successfully derives the laws of reflection and refraction of light. He was also successful in explaining the linear and spherical propagation of light using this theory. Thomas Young was born on June 13, 1773 and died on May 10, 1829. He was a British polymath who made notable contributions to the fields of vision, light, solid mechanics, energy, physiology, language, musical harmony, and Egyptology. He had a long rivalry with Egyptologist Jean-François Champollion on the decipherment of Egyptian hieroglyphs, specifically the Rosetta Stone. Augustin Jean Fresnel was born on May 10, 1788 and died on July 14, 1827. He was a French civil engineer and physicist whose research in optics led to the almost unanimous acceptance of the wave theory of light, excluding any remnant of Newton's corpuscular theory, from the late 1830s until the end of the 19th century. He is perhaps better known for inventing the Fresnel lens and for pioneering the use of step lenses to extend the visibility of lighthouses, saving countless lives at sea. In 1803, the experiment conducted by Thomas Young on the interference of light proved the Huygens wave theory of light to be correct. He put forth several theoretical reasons supporting the wave theory of light, and he developed two enduring demonstrations to support this viewpoint. Later in 1815, Fresnel expressed Huygens' principle of secondary waves and Young's principle of interference in quantitative terms, and stated that light consists of sinusoidal waves. Fresnel gave the first satisfactory explanation of diffraction by straight edges. Including the first satisfactory wave-based explanation of rectilinear propagation, provided mathematical equations for Young's experiment, leading to the almost unanimous acceptance of the wave theory of light, excluding any remnant of corpuscular theory. All waves move energy from place to place without transporting the matter in the transmission medium if there is one. In physics, a transverse wave is a wave that oscillates perpendicularly to the direction of the wave's advance. In contrast, a longitudinal wave travels in the direction of its oscillations. Electromagnetic waves are transverse waves without requiring a medium. Sound waves do require a medium. Let's examine the case of a transverse sinusoidal wave propagating in one direction x. The displacement y is a function of both x and t, so we can sketch graphs of y versus x at a certain time and y versus t at a certain x position to understand the nomenclature used for waves. A is the amplitude, k is the wave number, w is the angular velocity, phi is the phase shift or phase angle. The amplitude is the distance between the peaks and the equilibrium position. The period t is the time separation between two peaks. The frequency f is the inverse of the period. The angular velocity omega is 2 times pi divided by the period. The wavelength lambda is the distance between two peaks. The wave number is 2 pi divided by the wavelength. The wave velocity v is the wavelength divided by the period. The phase angle phi is defined by the wave function value at a time of 0 and a position of 0. So the wave equation can be written as the velocity of the displacement is the acceleration of the displacement is the second-order spatial derivative of the displacement is which leads to the partial differential equation for a wave. Or using vectorial calculus notation. Magnetism was discovered a long time ago when people noticed that magnetite rocks attract iron. Chinese in the 11th century used a magnetic spoon as compass, improving the accuracy of navigation. Soon after, Europeans were using the invention. Hans Christian Ørsted was born on August 14, 1777 and died on March 9, 1851. He was a Danish physicist and chemist. André Marie Ampère was born on January 20, 1775 and died on June 10, 1836. He was a French physicist and mathematician. Ørsted discovered in 1820 that electric currents create magnetic fields similar to the ones created by permanent magnets. In the same year, Ampère showed that iron can be magnetized by inserting it in an electrically fed solenoid. Ampère found that the magnetism produced by permanent magnets and the magnetism produced by electromagnets are the same kind of magnetism. The modern version of the equation proposed by Ampère for the electromagnetic field is, where J is the electric current density and μ0 is the medium permeability. We will see later that this equation is incomplete and another term will be added. Today we know that electricity and magnetism are in reality just one phenomenon known as electromagnetism. But Coulomb's law of electric attraction was ingrained in science. Today we also know that this force is better called electrostatic force since it is only valid when the charges are not moving. This posed a problem, since when charges move in an electric field and we assume the electric effect are only electrostatic, a fictitious force must be added. We call this the magnetic force. The magnetic force is the part of the electromagnetic field that affects moving charges. A magnetic field B is defined in order to correct the force acting on a moving charge in an electric field while accounting for the electrostatic force due to the electric field. This is expressed by Lorentz force law, where E is the electrostatic field, V is the velocity vector. The cross product of the velocity vector with the magnetic field gives the magnetic force component of the electromagnetic field. The direction of the magnetic field, velocity and force follow the right-hand rule as shown in this picture. It wasn't until the late 18th century that scientists began to develop a mathematical basis for understanding the nature of electricity and magnetism. Carl Friedrich Gauss was born on April 30, 1777 and died on February 23, 1855. He was a famous mathematician from Germany. Michael Faraday was born on September 22, 1791 and died on August 25, 1867. He was an English physicist and chemist. André Marie Ampère was born on January 20, 1775 and died on June 10, 1836. He was a French physicist and mathematician. James Clerk Maxwell was born on June 13, 1831 and died on November 5, 1879. He was a Scottish physicist and mathematician who was responsible for the classical theory of electromagnetic radiation, which was the first theory to describe electricity, magnetism and light as different manifestations of the same phenomenon. Maxwell's equations for electromagnetism are seen as the second great unification in physics, where the first one had been realized by Isaac Newton. Maxwell was also key in the creation of statistical mechanics. Faraday developed the law of induction. This is a law of electromagnetism predicting how a magnetic field will interact with an electric circuit to produce an electromotive force. This phenomenon, known as electromagnetic induction, is the fundamental operating principle of transformers, inductors, and many types of electric motors, generators, and solenoids. Carl Friedrich Gauss published in 1867 a law relating the electric flux through a surface and the electric charge density inside that surface. Gauss' law can also be applied to magnetic flux and magnetic charge density, which is zero. This second law is very similar to the first but applies to magnetic rather than electric fields. Ampere-Maxwell law is a little like Faraday's law, but it deals with changing electric flux. This process culminated in 1873 with the James Clerk equations published in his work A Treatise on Electricity and Magnetism. Maxwell improved and generalized many of the previous equations. His work included 20 equations and 20 variables using quaternions. Josiah Willard Gibbs was born on February 11, 1839 and died on April 28, 1903. He was an American scientist who made significant theoretical contributions to physics, chemistry, and mathematics. His work on the applications of thermodynamics was instrumental in transforming physical chemistry into a rigorous deductive science. Together with James Clerk Maxwell and Ludwig Boltzmann, he created statistical mechanics. Oliver Heaviside was born on May 18, 1850 and died on February 3, 1925. Gibbs and Heaviside independently developed vector calculus near the end of the 19th century. Its use allowed the concise form of today's Maxwell-Heaviside equations. Today, Maxwell's equations are a set of 4 partial differential equations which provide a complete description of classical electromagnetic fields. We will now conduct mathematical manipulations of Maxwell equations. Taking the curl of Faraday law yields, or vector calculus gives us the following identity. Which when combined with the previous equation yields. According to Gauss' law, in the absence of a charge. So we have, using Ampere's law, combining those equations in the absence of a current J, we obtain, or similar process yields for the magnetic field. We can easily recognize that those are wave equations for E and B, which tells us that there are waves traveling with speed v given by. Those waves are self-sustaining. A changing electric field is produced by moving a charged particle backwards and forwards. Then this changing electric field will produce a changing magnetic field. The changing magnetic field would then also produce a changing electric field, and this cycle could be repeated infinitely. Based on his equations, Maxwell predicted the existence of self-sustaining electromagnetic waves. The electromagnetic radiation would be self-propagating and would extend outwards into space as an electromagnetic wave of a fixed frequency. Further to this, both the electric and magnetic fields would necessarily oscillate at the same frequency. This speed calculated from the vacuum parameters so closely matched experimental values for the speed of light that it led him to the idea that light was a form of electromagnetic radiation. Like all great scientific breakthroughs, Maxwell's light bulb moment was not the end of the story. In getting the speed of light out of the equations of electromagnetism, he set the scene for the inevitable discovery of radio waves, gamma rays, X-rays, ultraviolet, visible, infrared radiation, microwaves. All were determined to be electromagnetic radiation differing only in their range of frequencies. The fact that the speed of light, electromagnetic waves, was constant and absolute, not relative, was in direct contradiction to the ideas of the time regarding relative velocities. It led to intense discussion, only resolved by Einstein with special relativity. Einstein realized that Maxwell's equations not only predicted that electromagnetic waves would move at the speed of light, but also that their speed would be constant, and constant in a subtle way that had eluded everyone before him, including Maxwell. The The electromagnetic spectrum is a continuous distribution of electromagnetic waves based on their frequency or wavelength and energy. The first person to explain that white light was made up of the colors of the rainbow was Isaac Newton, who in 1666 passed sunlight through a narrow slit, then a prism, to project the colored spectrum onto a wall. Newton clarified the situation by using a second prism to reconstitute the white light, making much more plausible the idea that the white light was composed of the separate colors. He then took a monochromatic component from the spectrum generated by one prism and passed it through a second prism, establishing that no further colors were generated. That is, light of a single color did not change color on refraction. He concluded that white light was made up of all the colors of the rainbow, and that on passing through a prism, these different colors were refracted through slightly different angles, thus separating them into the observed spectrum. Electromagnetic waves in the wavelength range of 389 to 769 nanometers are visible to the naked eye by humans. Even before Maxwell's work, there was knowledge of an invisible light. Frederick William Herschel was born on November 15, 1738 and died on August 25, 1822. He was a German-British astronomer and composer. In early 1800, Herschel was testing different filters to pass sunlight through, and noticed that filters of different colors seemed to generate varying amounts of heat. He decided to pass the light through a prism to measure the different colors of light using a thermometer, and in the process, took a measurement just beyond the red end of the visible spectrum. He detected a temperature 1 degree higher than that of red light. Further experimentation led to Herschel's conclusion that there must be an invisible form of light beyond the visible spectrum. He published these results in April 1800, calling it heat rays. What he discovered was the infrared light that has a between 400 terahertz to 300 gigahertz. Johann Wilhelm Ritter was born on December 16, 1776 and died on January 23, 1810. He was a German chemist, physicist and philosopher. Johann Ritters conducted experiments exposing photographic paper to light. In 1801 he observed that invisible rays just beyond the violet end of the visible spectrum darkened silver chloride-soaked paper more quickly than violet light itself. He called them deoxidizing rays to emphasize chemical reactivity and to distinguish them from heat rays, discovered the previous year at the other end of the visible spectrum. The terms chemical rays and heat rays were eventually dropped in favor of ultraviolet and infrared radiation, respectively. Heinrich Rudolf Hertz was born on February 1857 and died on January 1, 1894. He was a German physicist who first conclusively proved the existence of the electromagnetic waves predicted by James Clerk Maxwell's equations of electromagnetism by experimentally generating Hertzian waves in his laboratory in 1887, showing that they exhibited the same wave properties as light. The unit of frequency, cycle per second, was named the Hertz in his honor. The modern term radio wave replaced the original name Hertzian wave around 1912. Wilhelm Conrad Röntgen was born on March 27, 1845 and died on February 10, 1923. He was a German mechanical engineer and physicist. On November 8, 1895, Wilhelm Röntgen stumbled on X-rays while experimenting cathode tubes and began studying them. Röntgen referred to the radiation as X, to indicate that it was an unknown type of radiation. Röntgen discovered their medical use when he made a picture of his wife's hand on a photographic plate formed due to X-rays. Röntgen earned him the inaugural Nobel Prize in Physics in 1901. Paul Ulrich Villard was born on September 28, 1860 and died on January 13, 1934. He was a French chemist and physicist. Paul Villard discovered gamma radiation in 1900, while studying radiation emitted from radium. Villard knew that his described radiation was more powerful than previously described types of rays from radium, which included beta rays and alpha rays. However, Villard did not consider naming them as a different fundamental type. In 1914, gamma rays were observed to be reflected from crystal surfaces, proving that they were electromagnetic radiation. Rutherford and his co-worker Edward Andrade measured the wavelengths of gamma rays from radium, and found they were similar to X-rays, but with shorter wavelengths and thus, higher frequency. All wavelengths from UV, ultraviolet, to gamma range have the potential to ionize tissues and/or DNA. longer wavelengths and do not have the potential to ionize tissues and/or DNA. Antoine-Henri Becquerel was born on December 15, 1852 and died on August 25, 1908. He was a French engineer and physicist. Maria Salomea Skłodowska-Curie was born on November 7, 1867 and died on July 4, 1934. She is known simply as Marie Curie. She was a Polish and naturalized French physicist and chemist who conducted pioneering research on radioactivity. She was the first woman to win a Nobel Prize, the first person to win a Nobel Prize twice, and the first person to win a Nobel Prize in 2 scientific fields. Her husband, Pierre Curie, was a co-winner of her first Nobel Prize, making them the first married couple to win the Nobel Prize and launching the Curie family legacy of 5 Nobel Prizes. Becquerel had long been interested in phosphorescence, the emission of light of one color following the object's exposure to light of another color. Becquerel layered photographic plates with coins or other objects, then wrapped this in thick black paper, placed phosphorescent materials on top, placed these in bright sunlight for several hours. The developed plate showed shadows of the objects. Becquerel left some of his layered plates in a dark cabinet. He nevertheless proceeded to develop the plates, making an astonishing discovery. The object shadows were just as distinct when left in the dark as when exposed to sunlight. After other experiments involving non-phosphorescent uranium salts, he concluded that the penetrating radiation came from the uranium itself, without any need for excitation by an external energy source. There followed a period of intense research into radioactivity, including the determination that the element thorium is also radioactive and the discovery of additional radioactive elements polonium and radium by Marie Curie and her husband Pierre Curie. Intensive research of radioactivity led to Becquerel publishing 7 papers on the subject in 1896. The SI unit for radioactivity, the becquerel, is named after him. For work in this field he, along with Marie Curie and Pierre Curie, received the 1903 Nobel Prize in Physics. Ernest Rutherford continued Henry Becquerel experiments. The rays emitted by radioactive elements were named in order of their power to penetrate various materials, using the first 3 letters of the Greek alphabet, alpha rays as the least penetrating, followed by beta rays, followed by gamma rays as the most penetrating. After 5 years of additional experimental work, Rutherford and Hans Geiger determined that the alpha particle is a helium nucleus, 2 protons and 2 electrons. They interact with matter strongly due to their charges and combined mass, and at their usual velocities only penetrate a few centimeters of air, or a few millimeters of low-density material. Beta- radiation consists of an energetic electron. It is more penetrating than alpha radiation but less than gamma. Beta radiation from radioactive decay can be stopped with a few centimeters of plastic or a few millimeters of metal. Rutherford also noted that gamma rays were not deflected by a magnetic field, another property making them unlike alpha and beta rays. In 1914, gamma rays were observed to be reflected from crystal surfaces, proving that they were electromagnetic radiation and not particles, but the name gamma rays stuck. William Prout was born on January 15, 1785 and died on April 9, 1850. He was a physician interested in chemistry. Prout published 2 papers in 1815 and 1816 which he observed that the atomic weights that had been measured for the elements known at that time appeared to be whole multiples of the atomic weight of hydrogen. He then hypothesized that the hydrogen atom was the only truly fundamental object, which he called protyle, and that the atoms of other elements were actually groupings of various numbers of hydrogen atoms. Eugene Goldstein was born on September 5, 1850 and died on December 25, 1930. He was a German physicist. In 1886, Goldstein discovered anode rays and showed that they were positively charged particles produced from gases. However, Since particles from different gases had different values of charge to mass ratio, they could not be identified with a single particle, unlike the negative electrons discovered by Thomson. Wilhelm Wien was born on January 13, 1864 and died on August 30, 1928. He was a German physicist. In 1898, Wien identified the hydrogen ion as the particle with the highest charge to mass ratio in ionized gases. In 1917, Rutherford speculated that the hydrogen nucleus is present in other nuclei. Subsequently, Rutherford named this fundamental particle the proton. William Wollaston was born on August 6, 1766 and died on December 22, 1828. He was an English chemist and physicist who is famous for discovering the chemical elements palladium and rhodium. Joseph von Fraunhofer was born on March 6, 1787 and died on June 7, 1826. He was a German physicist and optical lens manufacturer. In 1801, Wollaston observed the sunlight through a prism in close detail, something that Newton did not. He noted that the spectrum was not continuous, and some wavelengths were missing. In 1817, Fraunhofer took an even closer look at the sun's spectrum by expanding the spectrum onto a large wall. As a result, he found thousands of slices that were missing. Gustav Kirchhoff was born on 12 March 1824 and died on October 17, 1887. He was a German physicist and chemist who contributed to the fundamental understanding of electrical circuits, spectroscopy, and the emission of black-body radiation. Robert Bunsen was born on March 30, 1811 and died on August 16, 1899. He was a German chemist. He investigated emission spectra of heated elements and discovered cesium in 1860 and rubidium in 1861 with the physicist Gustav Kirchhoff. The Bunsen-Kirchhoff Award for Spectroscopy is named after them. In 1859, by Kirchhoff and Bunsen witnessed that when certain chemicals were heated in Bunsen's burner, characteristic bright colors appeared. In some cases, these were at the same points in the spectrum as Fraunhofer's dark lines. These lines came to be known as spectral lines. It was speculated that excited atoms of elements were emitting radiation in those light frequencies. A light is considered to have a continuous spectrum, meaning it emits light across a broad range of wavelengths, including all visible colors, appearing as a continuous band when viewed through a prism. Emission lines refer to the fact that glowing hot gas emits lines of light. Whereas absorption lines refer to the tendency of cool gas to absorb the same lines of light. Emission and absorption spectra form the basis of spectroscopy, which uses spectra to provide information about the structure and the composition of a substance or an object. In particular, astronomers use emission and absorption spectra to determine the composition of stars and interstellar matter. Because the sun is very hot, the light it emits is in the form of a continuous emission spectrum. Superimposed on it, however, is a series of dark lines due primarily to the absorption of specific frequencies of light by cooler atoms in the outer atmosphere of the sun. The sun contains large amounts of helium, hydrogen, iron, and carbon, along with smaller amounts of other elements. Anders Ångström was born on August 13, 1814 and died on June 21, 1874. He was a Swedish physicist and one of the founders of the science of spectroscopy. Ångström is also well known for his studies of astrophysics, heat transfer, terrestrial magnetism, and the aurora borealis. Johann Jacob Balmer was born on May 1, 1825 and died on March 12, 1898. He was a math and Latin teacher at a girls' school in Basel, Switzerland. The spectrum of hydrogen atoms was first observed by Ångström in 1853. He noticed several lines on the hydrogen emission spectrum and determined 4 of their wavelengths. Angstrom had measured the 4 visible spectral lines to have wavelengths 656, 486, 434 and 410 nanometer. Balmer concentrated on just these 4 numbers, and found they were represented by the empirical formula. The expression given by Balmer matches very well with Angstrom measured values for the visible line spectra of hydrogen. Balmer predicted that other lines would occur in the ultraviolet light range for values of n larger than 6. The Balmer series extends to a limiting wavelength of 364.56 nanometers when n tends to infinity. Johannes Rydberg was born on November 8, 1854 and died on December 28, 1919. He was a Swedish physicist. Rydberg generalized Balmer's equation to determine the wavelengths of the lines in the hydrogen emission spectrum. Rydberg proposed the following equation for the hydrogen atom spectral lines. The values of N1 separate the hydrogen spectral lines into different series. For N1 of 1, it is called the Lyman series that lies completely in the ultraviolet range. For N1 of 2, it is the Balmer series with 4 lines in the visible range and the others in ultraviolet range. And for N1 of 3, it is the Paschen series that lies completely in the infrared range. The other named series are the Brackett series for N1 of 4, the Fund series for N1 of 5, and Humphreys series for N1 of 6. Further series are unnamed, but follow the same pattern and equation as dictated by the Rydberg equation. Series are increasingly spread out and occur at increasing wavelengths. The lines are also increasingly faint, corresponding to increasingly rare atomic events. For instance, the 7th series of atomic hydrogen was first demonstrated experimentally at infrared wavelengths in 1972 by Peter Hansen and John Strong at the University of Massachusetts Amherst. Those equations were empirical in nature without any theoretical justification, but they seem to provide insight into the structure of the atom. Today, it is known that the electromagnetic force between the electron and the nuclear proton in the hydrogen atom leads to a set of very specific states for the electron, each with its own energy. These states were visualized being distinct orbits around the nucleus. Each energy level is designated by an integer. Spectral emission occurs when an electron jumps from a higher energy state to a lower energy state. To distinguish the two states, the lower energy state is commonly designated as N1, and the higher energy state is designated as N2. The energy of an emitted photon corresponds to the energy difference between the two states. Because the energy of each state is fixed, the energy difference between them is fixed, and the transition will always produce a photon with the same energy. This is in contradiction with the Rutherford model of the atom that predicted a continuous spectrum for the photons when the electron changes its orbit. The contribution to our understanding of this phenomena came from scientists working in many different problems, but this will be covered in another video on quantum mechanics. For now, we will continue with the atom structure without quantum mechanics. We are already familiar with Rutherford. James Chadwick was born on October 20, 1891 and died on July 24, 1974. He was an English physicist who was awarded the 1935 Nobel Prize in Physics for his discovery of the neutron in 1932. In 1941, he wrote the final draft of the Maud Report, which inspired the US government to begin serious atom bomb research efforts. He was the head of the British team that worked on the Manhattan Project during World War II. William Draper Harkins was born on December 28, 1873 and died on March 7, 1951. He was an American physical chemist, noted for his contributions to surface chemistry and nuclear chemistry. Walter Wilhelm Georg Bothe was born on January 8, 1891 and died on February 8, 1957. He was a German nuclear physicist known for the development of coincidence methods to study particle physics. Irene Joliot-Curie was born on September 12, 1897 and died on March 17, 1956. She was a French chemist and physicist, the eldest child of Pierre and Marie Curie. With her husband, she was jointly awarded the Nobel Prize in Chemistry in 1935 for their discovery of induced radioactivity, making them the second ever married couple, after her parents, to win the Nobel Prize, while adding to the Curie family legacy of 5 Nobel Prizes. This made the Curies the family with the most Nobel laureates to date. Frédéric Joliot-Curie was born on March 19, 1900 and died on August 14, 1958. He was a French chemist and physicist, and the husband of Irene Joliot-Curie. Rutherford atom model consisted of a small positively charged massive nucleus surrounded by a much larger cloud of negatively charged electrons. It became soon clear to him, and others, studying nuclear disintegration, that the mass of the atoms are usually several times higher than its atomic number Z, the number of protons, and of electrons, in a neutral atom. He knew that the mass of an electron is much smaller than that of a proton. In 1920, Ernest Rutherford suggested that the nucleus consisted of positive protons and neutrally charged particles, suggested to be a proton and an electron bound in some way with a mass comparable to the mass of the proton in the nucleus, and that could account for the observed difference between the atomic mass A and the atomic number Z of an atom. About the time Rutherford suggested the neutral proton-electron composite, several other publications appeared making similar suggestions, and in 1921 Harkins first named the hypothetical particle a neutron. In 1928, Bothe bombarded beryllium with alpha particles emitted from polonium and found that it gave off a penetrating, electrically neutral radiation, which they interpreted to be high-energy gamma photons. In 1932, Irene Joliot-Curie and her husband, Jean Frederick, decided to use their strong polonium alpha source to further investigate Bothe's penetrating radiation. They found that this radiation ejected protons from a paraffin target. James Chadwick and Rutherford continue the investigation of this effect, with Rutherford very skeptic of the gamma photons theory. James Chadwick at the Cavendish Laboratory in Cambridge performed a series of experiments. He not only bombarded the hydrogen atoms in paraffin with the beryllium emissions, but also used helium, nitrogen, and other elements as targets. By comparing the energies of recoiling charged particles from different targets, he proved that the beryllium emissions contained a neutral component with a mass approximately equal to that of the proton. These properties matched Rutherford's hypothesized neutron. Chadwick won the 1935 Nobel Prize in Physics for this discovery that eluded Joliot and Curie with their wrong interpretation of their results. With this, the essential nature of the atomic nucleus was established, with the determination that neutron was a new elementary particle, distinct from the proton. The uncharged neutron was immediately exploited as a new means to probe nuclear structure, leading to such discoveries as the creation of new radioactive elements by neutron irradiation in 1934 and the fission of uranium atoms by neutrons in 1938. The discovery of fission led to the creation of both nuclear power and nuclear weapons by the end of World War II. Both the proton and the neutron were presumed to be elementary particles until the 1960s, when they were determined to be composite particles built from quarks. This will be explored in a later video on the Standard Model of Particle Physics.